Usually when we look at a building, whether it's a sleek new hospital or like a towering university research center, we tend to focus on the architecture.
Right, the design.
Yeah, the glass, the steel, the aesthetics. It feels static,
No.
permanent.
It feels like a finished product. I mean, we assume safety is just, well, baked into the bricks and mortar from day one.
Exactly. But then you step into the world of chemical laboratories and you open up a document like the 2019 edition of NFPA 45, and suddenly that static building isn't static anymore.
Not at all.
At first glance, this NFPA standard is a dense, highly technical manual. I mean, it is the standard on fire protection for laboratories using chemicals. It sounds completely dry.
Oh, it sounds like something meant strictly to be shoved in the bottom drawer of an engineer's desk.
Right, but when you actually start reading the source material, it's something much more thrilling. It is like a living blueprint for survival, and here's the sobering part. Almost every single rule in this book was written in the ashes of past mistakes.
Yeah, it is the absolute definition of institutional memory. Every mandate, every restriction, it represents a moment where theory met catastrophic reality.
Wow.
It's a physical embodiment of the engineering community looking at a smoldering foundation and saying, never again.
That is heavy. So, for you listening, today our mission on this deep dive is to unpack this fascinating document. We are going to trace its historical evolution, which honestly is a wild ride in itself.
Highly wild.
We're going to outline exactly what engineers and building owners absolutely must know when they are designing fire protection systems for these high-stakes environments. And most importantly, we are going to share the gripping, real-world stories buried deep in the annexes of this text.
The stories are incredible.
Yeah, stories about what actually happens when the physics of a chemical reaction outsmarts the blueprints on the table. So, okay, let's unpack this. Reading a fire code like this is kind of like looking at the rings of a tree, right?
That's a great way to put it.
You can see exactly what years the metaphorical and literal fires happened based on how the rules adapted and thickened. So, if we go back to the genesis of this standard, we're looking at the early 1970s. Paint a picture for me. What was the landscape of laboratory safety before this standard even existed?
Well, if we rewind to the early 70s, laboratories were this massive gray area in the world of fire protection engineering. You have to remember the context of the era, right?
Okay.
We had robust codes for heavy industrial manufacturing places with massive 1,000-gallon vats of flammable liquids. And we had robust codes for standard office buildings where, the biggest fire risk was a wastebasket full of paper.
Right, pretty low stakes.
Exactly. But a chemistry lab sits awkwardly in the middle. They aren't purely industrial, but they certainly aren't offenses. They are unique environments where highly reactive, flammable, and toxic materials are manipulated daily, but on what the code defines as a laboratory scale.
Wait, let me stop you there. What exactly does laboratory scale actually mean? Are we talking about test tubes, like little beakers?
The code defines it very specifically. Laboratory scale means containers designed to be easily and safely manipulated by one person.
Okay.
So we are not talking about forklift-sized drums. We're talking about glass jugs, liters of solvents, small pressurized gas cylinders.
That seems like it wouldn't be enough to take down a whole building, though. I mean, if I drop a glass jug of ethanol, it's a bad day for the floor. But it doesn't seem like an apocalyptic event.
And that assumption is exactly why the gray area was so dangerous. It's not the volume of a single container. It's the sheer variety and density of different reactive chemicals placed in close proximity.
Oh, I see.
Yeah, a single drop jug might not be catastrophic on its own, but if that spilled solvent flows across a bench and hits an ignition source, say a Bunsen burner or a faulty electrical outlet.
Which are everywhere in a lab.
Exactly. And then the resulting fire reaches a shelf holding metallic sodium, which explodes violently when exposed to water from a standard sprinkler system. Suddenly you have a compounding disaster.
Oh, okay.
So in 1974, the Technical Committee on Chemistry Laboratories tentatively adopted the very first edition of this standard, which officially became NFPA 45 in 1975. A lot of credit for that foundational work goes to the late Russell H. Scott, who led the committee during those drafting stages. I mean, they essentially had to invent a brand new category of building protection.
So they write the first rule book in 75. I'm assuming it wasn't perfect right out of the gate. How long did it take for them to realize they needed to, drastically shift their approach?
Well, for the first couple of decades, the standard was constantly being tweaked. 82, 86, 91. They were reacting to new chemicals and new types of research. But if you look at those tree rings, a massive foundational shift occurs in the 1996
You see
edition.
that happened in 96.
That's when the committee explicitly clarified its core objective. They drew a hard line in the sand. The goal of the entire document was refined to ensure a fire is contained to the room of origin.
Wait, contained to the room of origin, not extinguished immediately. That feels like giving up ground. Like if I'm a firefighter, I want the fire out, not just trapped in a room.
It sounds counterintuitive, but it's a concept called compartmentalization, and it is crucial to understanding high-hazard architecture. You have to assume that in a laboratory setting, a fire might grow so quickly or involve chemicals so volatile that standard extinguishing methods might temporarily fail.
Or just take too much time to deploy safely.
Exactly. The 96 shift acknowledged that the priority isn't saving the workbench. It's sacrificing the room to save the structural integrity of the rest of the building.
Wow, sacrificing the room.
Yeah. And to do this, they began separating the requirements for the maximum allowable quantities of chemicals based on one critical factor, whether the lab was sprinklered or non-sprinklered.
I am genuinely surprised to hear the word non-sprinklered anywhere near the phrase chemical laboratory. Are you telling me that in the 1990s you could build a chemistry lab full of flammable liquids and just choose not to put overhead sprinklers in it?
You absolutely could, provided you kept the chemical quantities beneath a certain threshold and relied heavily on human intervention, like manual fire extinguishers or alternative compartmentalization.
That sounds like a terrible
It
idea.
was a ticking clock. The engineering community was realizing that relying on humans to safely mitigate a chemical fire with a handheld extinguisher was statistically a losing game. So by the 2000 edition, the code flat-out prohibited large, non-sprinklered labs.
Good.
If your lab was over 10,000 square feet and dealt with Class A, B, or C hazard levels, sprinklers were no longer a suggestion. And then, the true turning point hit in the 2004 edition. The standard mandated automatic extinguishing systems for all new laboratories. Full stop. No loopholes.
No grandfathering for new construction.
None.
I'm trying to picture the pushback from the construction industry on that. I mean, sprinklers are expensive. Why was 2004 the year they finally brought the hammer down? What changed in the engineering philosophy?
It was a realization that human error in a laboratory is not an anomaly. It is an inevitability. You cannot simply train researchers to a state of perfection and expect zero accidents. The chemistry is too complex, the variables are too numerous, and, human fatigue is a very real factor.
Yeah, grad students working on 4 hours of sleep.
Exactly. The 2004 mandate signifies a shift from reactive protection to deeply proactive protection. It acknowledges that when a chemical fire starts, the time between ignition and a completely unsurvivable environment can be measured in seconds, not minutes.
Seconds. Right.
You must have an automatic active suppression system ready to intervene the millisecond an event reaches a specific threshold.
Okay, so the standard evolves, it mandates sprinklers, it starts heavily pushing containment. The document we are looking at today is the 2019 edition. What are the major modern upgrades? Because we were living in a vastly different world than 2004.
Oh, the evolution never stops. For example, the 2011 edition started heavily regulating multi-story buildings.
Why does being on the 5th floor change the math? A fire is a fire, whether it's on the ground floor or a skyscraper, right?
Think about the logistics of evacuation and fire department access. If a massive solvent fire breaks out in the basement or a ground floor, occupants can easily spill out into the street, and fire crews can blast water directly from the fire engines through the windows.
Oh, that makes sense.
Now put that same lab on the 10th floor of a high-rise. The occupants have to navigate stairwells, and the fire crews have to haul hundreds of pounds of gear up those same stairs.
Which takes precious time.
Exactly. The higher you go, the more difficult the fire is to fight. Therefore, the 2011 edition restricted the most dangerous, high-hazard labs depending on how high up in the building they were placed. Then, 2015 brought in specific, aggressively strict rules for educational and instructional labs.
I can completely see why. An instructional lab is essentially a room full of 19-year-old undergraduates who might be handling concentrated nitric acid for the first time in their lives.
Precisely. It's a terrifying thought for an engineer. And then we hit the 2019 edition. This version made 3 massive changes. First, it removed flat area limitations for hazard calculations in favor of a much more precise system based on volume and density limits.
Okay.
Second, it strictly limited hazardous chemical containers in active work areas to a maximum size of 20 liters.
20 liters, that's a little over 5 gallons, right? Like one of those big blue water jugs you see in an office dispenser. Why that specific number?
It is a direct mathematical response to modeling spill scenarios. If you allow someone to have a 50-gallon drum of acetone in their work area and it tips over, the resulting puddle surface area is so massive that the vapor generation rate would instantly overwhelm the room's exhaust system.
Creating a giant explosive atmosphere.
Exactly. By putting a hard cap at 20 liters, the code mathematically bounds the size of the worst-case scenario puddle on the floor. It ensures the resulting vapor cloud remains within the capacity of the ventilation system to extract it safely.
That is brilliant. And the third major change in the 2019 text.
It officially integrated healthcare facilities into the scope of NFPA 45.
Hold on. Hospitals have had clinical pathology laboratories, blood labs, and tissue testing facilities for decades. Are you saying they weren't regulated by fire codes before 2019?
Well, they were regulated, but primarily by NFPA 99, which is the Healthcare Facilities Code. But over time, engineers and fire marshals realized a fundamental flaw in keeping those regulations separate.
What was the flaw?
A highly flammable solvent like xylene, which is used constantly in tissue pathology labs, does not care about its zip code. It doesn't know if it's sitting on a titanium bench in a university chemistry department or in a hospital wing right next to a maternity ward.
A fire is a fire.
Right. A chemical hazard behaves according to the laws of thermodynamics, not zoning laws. Consolidating these clinical lab risks under NFPA 45 ensures that the most rigorous, specialized chemical fire protection standards are applied uniformly. It prevents dangerous gaps where a hospital lab might have been designed more like a standard patient care area rather than the high-hazard chemical environment it actually is.
So if a hospital is upgrading its pathology lab today, the architect has to open up this specific chemical laboratory manual, not just the hospital manual.
Exactly, which actually sets the stage for understanding the ultimate goal of all these mandates. Because if I am that hospital administrator or university president and I am spending $50 million outfitting a state-of-the-art research facility, I want to know exactly what this dense book of codes is doing for me.
I'm really glad you brought that up, because I imagine a lot of money changes hands based on what this text demands. Let's look at the true objectives of the code. What is NFPA 45 actually trying to protect? Because my assumption is that if I build a lab precisely to the 2019 code, my multi-million-dollar electron microscopes and my priceless cell cultures are perfectly safe from fire.
And this is where expectations violently collide with engineering reality. The explicit objectives of NFPA 45 are strictly, and I mean exclusively, about life, safety, and structural containment.
Just life safety.
Yes. There are three primary goals written directly into the foundational text. Objective 1, limit injury to the occupants at the point of fire origin. Objective 2, limit injury to emergency response personnel who have to enter the building. Objective 3, limit property loss to a maximum of a single laboratory unit.
A single laboratory unit, meaning the specific room or enclosed suite where the fire actually started?
Correct. And here is the crucial, devastating caveat that building owners must understand. Section 1.2.5 explicitly states, it is not the objective of this standard to address financial losses such as business interruption or property loss of a laboratory unit.
Wait, I'm trying to picture this. Let's say I'm an investor. I just spent $10 million on a robotic DNA sequencing lab. I hire an engineering firm. They build it exactly to NFPA 45 code. They get the permits. Everything is perfectly legal. A fire starts in a centrifuge. Are you telling me the fire code considers it a total success if my $10 million lab burns to ash, so long as the fire doesn't melt the walls and spread to the hallway?
That is exactly what I'm telling you. Think of the fire engineer's job as building a ship in a bottle. According to NFPA 45, their entire mission is to make sure that if a fire starts inside the bottle, the lab unit, it stays trapped inside the bottle.
Wow.
The goal is to ensure the rest of the ship, the wider building, survives, and the people inside the bottle have enough time to run out the neck. The code explicitly does not care if the ship inside the bottle is incinerated.
If I'm an owner, I'd be absolutely furious to find that out after a fire. Like, what do you mean code compliant doesn't mean my business is safe?
Right. And if we connect this to the bigger picture, this is perhaps the most vital, difficult conversation that a design engineer must have with their client at the very beginning of the schematic design phase. Owners constantly hear the phrase code compliant and mistakenly translate that to perfectly safe from all harm.
Which is a natural assumption.
It is. But they assume their intellectual property, their decades of research, their expensive equipment, is insulated. It is not. Code compliance is the absolute legal floor. It is the bare minimum standard required by the government to ensure you don't kill the humans inside or collapse the structure onto the street.
So what do they do if they want to protect the research?
If an owner wants to protect their equipment and prevent a 3-year business interruption, they have to open their wallets and go significantly above code. They must ask the engineer for specialized clean agent suppression systems, incredibly tight compartmentalization, or advanced early warning air sampling detection that NFPA 45 simply does not strictly require.
So the code is basically saying, we will keep you alive, but we won't keep you from going bankrupt. That is a massive paradigm shift in how people view safety regulations. So to manage this ship-in-the-bottle concept, how do engineers actually know how thick to make the walls of the bottle?
They have to design around strict hazard classifications. NFPA 45 breaks laboratory units down into 4 highly regulated classes. Class A is defined as a high fire hazard. Class B is a moderate fire hazard, Class C is low, and Class D is minimal.
Okay, my instinct would be to classify them by the type of work they're doing. Like, a virology lab studying pathogens is Class A, but a geology lab looking at rocks is Class D. Is that how it works?
No, actually, it is entirely disconnected from the type of research being conducted. The virology lab and the geology lab could both be Class A or both be Class D. The classification is purely mathematical.
Really?
Yes, it is based entirely on the volume and density of flammable and combustible liquids permitted within that specific enclosed laboratory unit.
Walk me through the math on that. How does an engineer calculate that?
The code provides incredibly detailed matrices, specifically tables 9.1.1a and b. These tables dictate exactly how many gallons of Class 1, 2, or IIU liquids you are legally allowed to possess per 100 square feet of lab space, and what the absolute maximum cap per unit is.
What are the classes of liquids?
So Class I liquids are your highly volatile flammables, like diethyl ether or acetone, which can ignite at room temperature. Class 2 and IPAA are combustibles, like diesel fuel or certain oils, which require a bit more heat to ignite. The engineer looks at the architectural floor plan, measures the square footage of the room, and runs the multiplier.
So they just multiply the space by the loud density?
Exactly. If the client says, we need to store 400 gallons of acetone in this 2,000 square foot room, the engineer runs the math against the table and says, congratulations, you are now a Class A high hazard laboratory.
And I imagine once you trigger that Class A designation, the building requirements become astronomically expensive.
Oh, the architectural demands change instantly. For instance, the code states that Class A or B labs, the high and moderate hazards, are outright prohibited from being located below grade. You cannot put them in a basement.
Why not a basement? It seems like a basement would be a great place to trap a fire. It's surrounded by dirt.
It's terrible for ventilation, though. Remember those heavier-than-air flammable vapors we talked about?
Oh, right. They sink.
Exactly. If you have a massive solvent spill in a basement, the vapors pool. They can't vent out windows. They seek out ignition sources like water heaters or electrical panels. Furthermore, if a fire happens, the fire department has to descend into an oven, fighting against the natural upward flow of heat and toxic smoke. It's a total death trap.
That makes total sense.
Furthermore, if you put a Class A lab on an upper floor, say the 3rd floor, it requires a 2-hour fire-rated separation from the rest of the building.
I've always wondered about this. 2-hour fire-rated walls. If a chemical fire fueled by hundreds of gallons of acetone is burning at over 1,000 degrees Fahrenheit, how does drywall or steel possibly hold back that inferno for 2 full hours? What is actually inside that wall?
It's a marvel of material science. It's not just standard drywall. A 2-hour rated wall is an assembly. It typically involves multiple layers of specialized Type X or Type C gypsum board on both sides of heavy-gauge steel studs. But here is the secret: gypsum inherently contains water molecules bound within its crystalline structure, roughly 21% by weight.
Water inside the drywall.
Yes. When exposed to extreme fire temperatures, this water is slowly released as steam, a process called calcination. This phase change absorbs massive amounts of thermal energy, keeping the opposite side of the wall relatively cool.
That is wild.
Until all that chemically bound water is boiled away, the wall won't transmit the lethal heat. The 2-hour rating literally means the wall will undergo calcination for 2 full hours before the structural integrity fails or the heat transfers enough to ignite something on the other side.
That is fascinating. The wall is essentially sweating to cool itself down. Now, you mentioned earlier that the rules change dramatically for places where students are involved.
Yes, the rules for educational and healthcare labs are aggressively strict. Remember those 4 classes, A, B, C, and D. An instructional laboratory like a high school chemistry classroom or a university undergraduate chemistry 101 lab must be classified as Class C or D. Furthermore, an educational lab is only legally permitted to contain 50% of the flammable liquids allowed in a standard commercial Class C lab.
It's basically a legally mandated child-proofing system. You are acknowledging that a room full of college freshmen is inherently more unpredictable than a room full of PhD researchers. You can't control the human error, so you drastically lower the amount of fuel they have access to. You minimize the potential energy in the room.
Exactly. You are lowering the ceiling on the worst-case scenario.
So if the goal is containing the fire to the bottle, and we have mathematically classified exactly how dangerous the bottle is allowed to be, how does the engineer physically build the room to fight the fire? Because putting up a sweating gypsum wall is passive protection. It just stands there. What about the active systems? This isn't just about throwing a standard sprinkler head in the ceiling and calling it a day, is it?
Not at all. The mechanical engineering required for chemical laboratories is incredibly specialized. Let's start with the sprinkler mandates. As we established, all new labs require automatic sprinklers. But the code dictates the sheer volume of water required based on your hazard class. If you were designing a Class A or B lab, you must install an ordinary hazard Group 2 sprinkler system. Class C and D require Group 1.
What does Group 1 versus Group 2 actually mean in the real world? Are the pipes bigger?
It dictates the design density of the water flow. It's measured in gallons per minute per square foot over a specific assumed operating area. An ordinary hazard Group 2 system is designed to dump a significantly higher density of water onto the fire because the engineer must assume the fire will involve volatile liquid fuels that generate immense heat.
So it's basically a heavier downpour.
A much heavier downpour. The pipes are often larger, the water pressure demands are higher, and the pump supporting the system has to be much more robust. But the most critical mandate in Section 6.1.1.2 is the specific type of sprinkler head required. The code mandates the use of quick response, or QR sprinklers.
How does a QR sprinkler differ from the standard sprinklers I see looking up at the ceiling in an office building or like a grocery store?
To understand the difference, you have to look at the anatomy of a sprinkler head. Most sprinklers are held shut by a small glass ampoule, a little bulb filled with a glycerin-based liquid. This liquid is designed to expand as it heats up.
Okay.
When the ambient temperature near the ceiling reaches a specific point, often 155 or 165 degrees Fahrenheit, the liquid expands so much that it shatters the glass bulb. This releases the plug, allowing the pressurized water to hit the deflector plate and spray across the room.
So what makes the quick response version faster? Does it use a different liquid?
It's simpler than that. It's about thermal mass. In a standard response sprinkler, the glass bulb is about 5 millimeters thick. It takes a certain amount of time for the heat of the fire to penetrate that thick glass and heat the liquid inside. A quick response sprinkler uses a much thinner 3 millimeter glass bulb.
Oh, I see.
Because there is less glass mass to absorb the heat, the glycerin liquid heats up and shatters the bulb significantly faster.
So we are talking about a difference in response time of seconds. Does a few seconds really matter when a fire breaks out?
In a laboratory, those seconds are the difference between life and death. And we know this because the National Institute of Standards and Technology NIST conducted extensive live burn fire tests in replica chemical laboratories to evaluate this exact dynamic.
What do they find?
They found that standard response sprinklers eventually controlled the fire, but they took too long to activate. By the time the 5 millimeter glass shattered, the heat and toxic smoke layer banking down from the ceiling had already rendered the room unsurvivable.
Wait, I am trying to visualize this. When a fire starts, the smoke doesn't just fill the room evenly, right? It goes straight up.
Yes. The superheated toxic gases from a chemical fire rise rapidly to the ceiling and then begin banking down, creating a distinct, highly lethal thermal layer. NIST tests proved that the 3 millimeter QR sprinklers activate fast enough to physically drive that heat layer back up, cooling the gases before they can bank down to the floor. The code specifically notes that QR sprinklers maintain what they call tenability at the 5-foot level in the room of origin.
Tenability is such a clinical engineering word for survivability. And that 5-foot mark, that's not a random architectural benchmark. 5 feet is roughly the breathing zone for a crouching human trying to frantically escape a burning, smoke-filled room.
That is exactly what it is. The QR sprinklers are engineered to activate so quickly that they literally carve out a pocket of breathable, survivable air for a human in a panic. If a researcher's ducking down at that 5-foot mark, the QR system ensures their lungs aren't seared by superheated gases before they can reach the exit door.
That is incredible. The mechanical system is literally manipulating the thermodynamics of the room to save a fleeing life. But here is where it gets really interesting and where I get confused. What happens if the lab uses chemicals that react violently with water?
Ah,
What if the researcher is working with alkali metals, like sodium or potassium? If I remember high school chemistry, dropping water on pure sodium creates hydrogen gas and an immediate explosion. If the ceiling opens up and dumps hundreds of gallons of water onto a sodium fire, you haven't put out the fire, you've created a bomb.
you've hit on one of the most complex challenges a fire protection engineer faces. They cannot just blindly draft a water sprinkler system and walk away. They have to interrogate the client. They must know exactly what chemical inventories will be in that lab before a single pipe is drawn on the blueprints.
Because water could make it worse?
Much worse. If introducing water creates a severe life safety or explosion hazard, NFPA 45 provides provisions for alternative, non-water automatic extinguishing systems.
Like what? Do they just dump foam into the room?
Foam is one option, but it still contains water. For highly water-reactive environments, engineers might specify dry chemical systems or clean agent systems, which are gaseous fire suppressants that replace the old ozone-depleting halon systems. Or, in very specific cases, total flooding carbon dioxide systems.
A total flooding carbon dioxide system, meaning it literally floods the entire room with CO2 to choke out the fire by removing the oxygen.
Exactly. It rapidly displaces the oxygen in the room. The fire suffocates instantly.
But if you displace all the oxygen to suffocate the fire, wouldn't you also suffocate the chemist who is trying to escape the room?
Yes, a total CO2 dump in an occupied room is lethal. Therefore, the engineering of the alarm and evacuation sequencing must be absolutely flawless. The system is designed with pre-discharge alarms. A loud horn and strobe go off, warning the occupants that the room is about to become an oxygen-free zone, giving them a calculated window of time, usually 30 to 60 seconds, to evacuate before the massive gas cylinders release the CO2. It requires intense safety protocols and training to ensure nobody's trapped inside.
It is a massive puzzle of risk management. Now, beyond the sprinklers and the clean agents, the outline for this code mentions standpipes. What role do they play in a modern lab?
Section 6.3 mandates class on wet standpipes for laboratory buildings, where the highest floor is over 30 feet above fire department vehicle access, or 30 feet below it.
Why 30 feet? Is that the maximum reach of a fire engine's ladder, or like the physical limit of dragging a hose?
It's primarily about friction loss and deployment time. Water is heavy. Dragging a charged, water-filled fire hose up 3 or 4 flights of stairs is physically exhausting and incredibly time-consuming. Furthermore, every foot of hose creates internal friction against the water flowing through it, which drops the pressure at the nozzle.
Oh, I never thought about that.
Yeah, if a fire crew has to run 200 feet of hose up 4 flights of stairs to reach a burning chemistry lab, by the time they get there, they might not have enough pressure to penetrate the fire, and the fire has had an extra 10 minutes to grow. A standpipe system solves this.
So a standpipe is essentially a heavy-duty permanent water main built vertically into the stairwells of the building.
Exactly. The building's internal fire pumps keep it pressurized. When the fire department arrives, they don't drag hoses off the truck and run them up the stairs. They carry folded, dry hoses up to the floor beneath the fire, plug directly into a massive brass valve on the standpipe in the stairwell, crack it open, and fight the fire from there. It shaves critical minutes off their response time.
Okay, so we have QR sprinklers cooling the air, we have alternative gas systems for reactive metals, we have standpipes for the fire crews. What about the aftermath? Let's say the sprinklers go off, they dump 1,000 gallons of water into the lab, and that water mixes with whatever solvents and acids spilled during the fire. I'm imagining a highly toxic, corrosive, and potentially flammable soup spreading across the floor.
You're imagining exactly what keeps environmental engineers awake at night. That brings us to section 5.1.5 of the code, which is floor sealing. The code explicitly requires that floors, floor openings, and penetrations must be completely sealed or curbed to prevent liquid leakage to lower floors.
Because if you have an office suite on the floor below the lab, you don't want a toxic waterfall pouring out of the ceiling fixtures onto someone's desk.
Exactly. And it's not just about offices below. It's about electrical rooms, server rooms, and elevator shafts. If corrosive chemicals leak into an elevator shaft, it destroys the hoisting cables and the electrical relays. The floor of a chemical laboratory must act as a watertight basin. And crucially, the caulks, sealants, and curbing materials used to seal the floor must be chemically compatible with the substances used in the lab. You cannot use a standard silicone caulk if the lab uses solvents that will instantly dissolve silicone.
So the overall containment strategy is completely holistic. The engineer is containing the physical flames with 2-hour calcining gypsum walls. They are containing the lethal heat layer with quick response sprinklers. And they are containing the chemical runoff by turning the floor into a sealed bathtub. It means the engineer has to be part chemist, part architect, and part psychologist predicting human panic.
That's an incredibly demanding job.
But engineering these systems perfectly on paper is one thing. What happens when the clean lines of a blueprint meet the chaotic reality of a real fire? Let's talk about the real-world consequences and the paradoxes within the code, because the annexes of NFPA 45 don't just tell you what to do, they tell you the horrifying stories of why you must do it.
The historical case studies embedded in the annex are arguably the most valuable part of the standard. They challenge everything standard engineers are taught. And there is no better example of a laboratory paradox than the 2001 University of California fire.
Tell me about this fire, because the lessons learned from it completely upended how we handle HVAC ductwork.
In 2001, a massive fire broke out in a multi-story chemistry laboratory at a University of California campus. It caused roughly $3.5 million in damage. But the most interesting part of the story wasn't the fire itself. It was what the post-fire investigators discovered when they arrived to sift through the wreckage and figure out what went right and what went wrong.
To understand why their discovery was so shocking, we have to understand how a normal building's air high-rise office building and a fire starts on the 5th floor. My understanding is that the HVAC ducts are equipped with fire dampers.
Yes. A fire damper is a heavy-duty galvanized steel louver built right into the ductwork where it passes through a fire-rated wall. Under normal conditions, the louver is held completely open by a device called a fusible link, which is two small pieces of metal soldered together with an alloy that melts at a very specific low temperature, usually 165 degrees.
So when the hot smoke from the office fire travels into the duct, the hot air hits the fusible link, the solder melts, and a heavy spring violently snaps the steel louvers shut, completely sealing off the duct.
Exactly. The entire philosophy of standard HVAC fire protection is to isolate the fire. You shut the dampers, choke off the air supply so the fire loses oxygen, and prevent the smoke from traveling through the ductwork to poison people on the 6th and 7th floors. It is Building Code 101. But in the 2001 UC lab fire, investigators found that the laboratory exhaust ducts did not have fire dampers. The ducts stayed wide open during the entire inferno.
Wait, the ducts stayed open, meaning it was pulling oxygen into the fire and pulling smoke out, and you're saying that helped. My instinct is that feeding a fire constant oxygen is the absolute worst thing you can do.
In a standard office, yes. But a chemical laboratory is not a standard office. The investigators realized that the exhaust system, the massive fans on the roof that pull air out of the fume hoods, kept running during the fire. Because there were no dampers to snap shut, the system acted like a giant industrial vacuum cleaner.
Oh, wow.
Yeah, it sucked the immense volume of toxic explosive combustion products along with the unburned flammable chemical vapors right out of the burning room, pulled them up the shaft, and vented them safely into the atmosphere high above the roofline.
So instead of trapping the explosive gases inside the room, it was continuously purging them.
Precisely. The investigators explicitly noted in their report that if a window in the lab hadn't eventually shattered, which allowed a massive rush of fresh makeup air to flow into the room and feed the draft, the situation would have been catastrophically worse. If a damper had snapped shut, the flammable solvent vapors would have rapidly accumulated inside the sealed lab until they hit their explosive limit. The entire room would have detonated, blowing out the structural walls.
Because of this specific real-world event, does NFPA 45 now forbid the use of fire dampers?
Yes. Section 7.5.1.2 is crystal clear. Automatic fire dampers shall not be used in laboratory exhaust systems. Furthermore, the controls for the exhaust fans must be designed to fail open.
Fail open.
Yes. This means if the fire burns through the electrical conduits and the system loses power, mechanical fail-safes force the exhaust valves to remain wide open, ensuring a continuous draft is maintained via the natural stack effect of the hot air rising up the shaft.
I love this detail because it highlights the friction between general engineering and specialized engineering. If I'm an HVAC engineer fresh out of school and I'm hired to design a lab, my muscle memory tells me to install fire dampers to stop the smoke. But if I apply standard office building logic to a chemical lab, I am inadvertently building a bomb. I am sealing explosive vapors inside a box. It's a completely inverted paradigm.
It proves why NFPA 45 is a distinct standard. The rules of engagement change entirely when volatile chemicals are introduced. And speaking of explosions, the code details another harrowing incident that changed the rules regarding premixing chemicals. Let's look at the 2016 explosion referenced in Annex 8011.900.1.5.
What happened in 2016?
A postdoctoral researcher was conducting an experiment that involved a gas mixture of hydrogen, oxygen, and carbon dioxide.
Hydrogen and oxygen. Are you kidding me? That is the literal stoichiometric mixture used to propel rockets into space. It is incredibly unstable.
Exactly, and they were manipulating it in a standard laboratory setting. Due to an ignition source or an overpressure failure within the experimental apparatus, the mixture detonated. The force of the explosion was catastrophic. It seriously injured the researcher, causing severe trauma, and it absolutely destroyed the laboratory infrastructure. The blast wave shattered equipment, compromised the walls, and blew out the windows.
A postdoctoral researcher is highly educated. How does something like this happen? Do they just eyeball the mixture and hope for the best?
Often, researchers become hyper-focused on the academic goal of the experiment, the data they're trying to collect, and they lose sight of the raw kinetic energy they're manipulating to get there. This tragic incident sparked a major operational update in the 2019 edition of the code.
What's the update?
The standard now requires a strict, formalized, and documented hazard analysis and risk assessment before conducting any experiments that involve the premixing of flammable and oxidizing materials.
So they can't just walk into the lab and start turning bells. They have to file paperwork proving they understand the physics of what they're about to do.
They have to mathematically evaluate the potential energy release. They must analyze the thermodynamics of the intended reaction, anticipate unintended side reactions, and physically prove to the safety committee that they have installed appropriate blast shielding, explosion venting, or engineered barricades to absorb an overpressure event if the mixture detonates. It forces the human brain to slow down and acknowledge the lethal potential of the chemistry.
It's an enforced pause. I can see how that would be critical for PhDs pushing the boundaries of science, but let's look at the opposite end of the spectrum. We talked earlier about educational labs, high schools, and undergraduate colleges. The code heavily restricts them. What kind of nightmares are documented regarding classrooms?
Annex A12.3.1 explicitly warns against the presence of bulk chemical quantities in instructional spaces. The annex documents cases where teachers or professors kept bulk containers, like 2-liter or 4-liter glass jugs of highly flammable solvents like methanol or ethanol on classroom benches during demonstrations.
A 2-liter bottle of methanol, that's a massive amount of highly flammable fuel sitting 3 feet away from a row of desks.
In several tragic cases, these large bottles were accidentally knocked over during a demonstration, or the vapors pouring out of the open neck were ignited by a nearby Bunsen burner. The resulting flash fires caused severe, life-altering third-degree burn injuries to both the instructors and the students.
Which leads to perhaps the most terrifying phenomenon I found while reading the code, a phenomenon known as flame jetting. I had never heard of this before. What exactly is a flame jet?
Flame jetting is a horrifying illustration of how human psychology works against us, combined with a brutal lesson in fluid dynamics. Imagine a high school science teacher doing a classic chemistry demonstration. They have a plastic or glass bottle of flammable liquid, say isopropyl alcohol. They want to pour a small amount into a crucible to light it on fire and show the class the flame. Our brains look at that small bottle and categorize it as relatively harmless. What's the worst that can happen? A little poof of flame on the desk.
Right, it's a bottle. I drink soda out of bottles. Doesn't register as a weapon.
That exact assumption is what gets people killed. The Bureau of Alcohol, Tobacco, Firearms, and Explosives, the ATF, conducted extensive high-speed camera testing on this phenomenon. They proved that if you have a necked container of flammable liquid, meaning the opening at the top is narrower than the main body of the bottle, and it lacks a specifically designed metal screen called a flame arrestor, that bottle can spontaneously transform into a weapon.
Walk me through the physics of this, because it is vital to understand how terrifying this is. What actually happens inside the bottle when it goes wrong?
When the bottle is open, flammable vapors are constantly mixing with the oxygen in the air inside the bottle, creating a combustible fuel-air mixture in the headspace above the liquid. If the teacher brings a flame or a spark too close to the open neck, the vapor inside the bottle ignites.
So the fire travels into the bottle
Instantly. And when a gas ignites, it rapidly expands. The pressure inside the body of the bottle spikes violently in a fraction of a second. That rapidly expanding burning gas has only one place to escape out the narrow neck of the bottle.
And because it's being forced through a narrow opening, it acts exactly like a rocket nozzle, the Venturi effect. The velocity of the burning gas accelerates dramatically.
A rocket nozzle is the perfect analogy. The ATF testing proved that this sudden pressure spike can generate a concentrated, high-velocity jet of burning liquid and supersonic flame that shoots out of the bottle's neck. Do you want to guess how far that flame jet can travel?
If it's a standard 2-liter bottle, maybe 3 or 4 feet, enough to burn the teacher's face.
Over 12 feet, or 3.05 meters.
12 feet from a plastic bottle.
Yes. A 12-foot horizontal column of fire traversing the classroom in a fraction of a second, spraying burning liquid across everyone in its path. It is an improvised flamethrower, and it happens so fast that no human reflex can dodge it.
That is absolutely chilling. A science teacher trying to show kids a cool blue flame could accidentally incinerate the front row of students.
It is horrifying, and it has happened multiple times, resulting in devastating lawsuits and horrific injuries, which is why the 2019 code mandates a strict spatial rule. Any experiment involving chemicals performed outside a fume hood without a blast shield must be located a minimum of 10 feet away from any students.
10 feet. Because the flame jet reaches 12 feet, the teacher is standing at the desk and the students are placed literally just outside the maximum calculated blast radius of an improvised flamethrower.
Exactly. These stories highlight a profound limitation of engineering. The building's architecture, the calcining gypsum walls, the quick-response sprinklers dropping the heat layer, the fail-open exhaust ducts, purging the vapors, can only do so much. At the end of the day-to-day operations and the split-second decisions made by the humans inside the lab are the ultimate arbiters of disaster.
Which brings us perfectly to our final major topic, the human element and daily operations. Because you can engineer the most technologically advanced, fire-safe building on the planet, but if a human makes a profoundly bad decision inside it, the entire system collapses. And NFPA 45 recognizes this, which is why Chapter 8 is completely unique compared to the rest of the book.
Chapter 8 covers chemical storage, handling, and waste disposal, and what makes it unique in the realm of fire codes is the concept of retroactivity.
Explain retroactivity. Why is that unusual?
Generally speaking, building codes only apply to new construction. If you built a laboratory in 1980 and it met the 1980 fire codes, the government generally does not force you to tear down the walls and rebuild the ventilation system to meet the 2019 construction standards unless you are undertaking a major permitted renovation. It's called being grandfathered in.
Because the cost of retroactively applying structural codes to every building in the country would bankrupt the economy?
Exactly. But Chapter 8 doesn't care when the building was built.
Wow.
Chapter 8 governs human behavior and daily operations, and you cannot grandfather in unsafe human behavior. The rules in Chapter 8 apply to every single existing laboratory, regardless of when it was constructed. If your lab was built in 1960, you still must follow the 2019 operational rules today.
So what kind of behaviors are we talking about regulating? We already touched on the 20-liter limit for hazardous chemical containers in active work areas to bound the spill size. But I want to talk about something that seems so mundane, yet the code treats it as a massive threat. The break room appliance that is secretly a bomb, the standard domestic refrigerator.
Ah, yes. The domestic refrigerator is a classic recurring violation in laboratory safety. Here is the scenario. A grad student or a researcher is working with a highly volatile, highly flammable solvent. They want to keep it cool so it doesn't evaporate as quickly, or perhaps the chemical requires cold storage to remain stable. So they walk down the hall, or they bring in a standard mini fridge from their college dorm room, plug it into the wall, and stick the flask of solvent inside.
It seems logical. It's a box that gets cold. What is the danger?
We have to look at the thermodynamics and the electrical engineering of a standard fridge. Flammable liquids, even when capped, often emit vapors. In a sealed, insulated box like a refrigerator, those vapors have nowhere to vent. They accumulate. Furthermore, cold vapors are dense and heavy. They sink. So inside this sealed fridge, you are slowly building a concentrated pool of highly explosive, invisible gas at the very bottom of the compartment.
Okay, so I have a pool of explosive gas at the bottom of the fridge, but it needs an ignition source. It's cold and dark inside.
It is not dark for long, and it is full of ignition sources. Think about how a domestic refrigerator operates. When you open the door, a mechanical friction switch releases, sending an electrical current to turn on the interior light bulb. That switch generates a microscopic electrical arc, a tiny spark.
Oh no.
Furthermore, at the bottom of the fridge, exactly where those heavy vapors are pooling, you have the thermostat dial clicking on and off, you have the defrost timer relay, and outside at the base, you have the compressor motor kicking on, vibrating, and generating heat and electrical arcs.
So the grad student puts the beaker in the fridge on Friday. Over the weekend, the vapors pool at the bottom. Sunday night, the thermostat clicks on, creating a tiny microscopic spark in the exact center of the vapor cloud.
Boom. The spark ignites the fuel-air mixture. The rapidly expanding gases blow the door of the refrigerator clean off its hinges, turning it into a high-velocity projectile. The resulting fireball ignites the rest of the lab. This has happened enough times that NFPA 45 explicitly mandates the use of specialized, explosion-proof or laboratory-safe refrigerators for storing any flammable liquids.
How does an explosion-proof fridge differ from my kitchen fridge?
The engineering is brilliant. First, all internal sparking devices are completely eliminated. There are no interior lights, no exposed thermostat dials, no mechanical switches inside the cold compartment. The compressor, the relays, and all electrical controls are moved to the exterior top of the unit, completely isolated and elevated far away from where heavy vapors would pool. Furthermore, they are designed with magnetic door gaskets instead of mechanical friction latches.
Why magnetic gaskets?
Because if a mild overpressure event does somehow occur inside, a magnetic gasket allows the door to simply pop open safely to vent the expanding pressure. A mechanical latch would hold the door shut until the pressure breached the structural integrity of the steel box, essentially turning the fridge into a shrapnel grenade.
It is engineering a solution to solve a very specific, stubborn human habit. But what about handling the chemicals themselves? The code has very specific rules about wardrobe, specifically dealing with pyrophoric reagents.
Pyrophoric reagents are some of the most dangerous materials handled in a laboratory setting. By definition, a pyrophoric chemical is a substance that will ignite spontaneously when exposed to air.
Wait, spontaneously, like no spark needed, no heat source.
None. No spark, no flame, no static electricity. Just the oxygen or the ambient moisture in the room air is enough to cause the chemical bond to break down violently, causing the substance to instantly burst into flames. Examples include certain organometallic compounds like tert-butyllithium.
If they burst into flames the second they touch air, how does a human being even work with them? How do you get them out of the bottle?
The code strictly mandates they must be handled inside inert atmosphere glove boxes. These are heavily sealed, transparent enclosures. The ambient air is completely purged and replaced with a dry, inert gas that cannot react with anything, usually argon or nitrogen. The researcher stands outside the box and sticks their arms into heavy rubber gloves built directly into the glass wall to manipulate the chemicals in a zero-oxygen environment.
But eventually you have to take the chemical out, right? You have to move it to a different machine or transfer it to a syringe.
Yes. Researchers use specialized SureSeal bottles and airtight syringes to transfer the liquids, but the risk of a spill or a needle slip is incredibly high. And if that liquid squirts out and hits the researcher, it immediately catches fire. Because of this, Section 6.6 of the code dictates exactly what a chemist is legally allowed to wear.
The fire code is dictating fashion.
It dictates survival. The code requires personnel handling these chemicals to wear specialized flame-resistant lab coats. But the crucial detail, the detail that saves lives, is what they must wear underneath the lab coat. They're strictly required to wear natural fiber clothing, cotton, wool, or silk.
So no synthetic athletic wear, no polyester, no nylon, no spandex blends.
Absolutely no synthetics. Let's look at the thermal dynamics of a clothing fire. If a pyrophoric liquid squirts onto your chest and ignites, the flame-resistant lab coat will not burn. But it is not a magical heat shield. It'll only buy you a few seconds. The intense heat of the chemical fire transfers directly to the fabric of the coat to the shirt underneath.
And if I'm wearing a polyester shirt under the coat?
Polyester is a thermoplastic. When exposed to high heat, it doesn't just burn, it melts. It turns into a boiling, sticky, molten plastic liquid. If you are wearing a synthetic shirt under your lab coat, the heat transfers through and the plastic fibers melt directly into your skin. It causes catastrophic, deep tissue thermal burns that merge with the flesh, making it incredibly difficult and agonizing for trauma surgeons to treat, as they have to physically cut the melted plastic out of the wound bed.
Good God, that is horrific.
It is. But if you are wearing a 100% cotton shirt, natural fibers will scorch and they will eventually burn, but they will never melt into the flesh. They ash away. It is a gruesome distinction, but it is a vital one that the code enforces to mitigate the severity of the injury.
And if a researcher does catch fire, the code tries to reprogram the most basic, primal human instinct, the instinct to run.
The Annex explicitly notes a tragic psychological reality. When humans catch fire, panic sets in instantly, and the instinct is to run away from the danger. But running just feeds the fire. You're forcing massive amounts of fresh oxygen over the flames, accelerating the burn rate. Running causes fatalities.
You learn it in kindergarten. Stop, drop, and roll.
Exactly. NFPA 45 reiterates that this simple childhood mantra must be trained into highly educated lab personnel until it is pure, overriding muscle memory. Because in a chaotic lab environment, the emergency safety shower might be 40 feet down a cluttered hallway. You will not make it. You must drop to the floor to prevent inhaling the superheated toxic gases rising to your face, and you must roll to smother the flames.
So, the engineering is the invisible safety net, but the human is the acrobat. Both have to perform perfectly, or the whole system fails. So what does this all mean for you, the listener? We've taken an incredible journey today through the 2019 edition of NFPA 45. We've seen its origins in the regulatory gray area of 1974. We've tracked its evolution from merely suggesting compartmentalization to aggressively mandating quick response sprinklers to precisely bounding puddle sizes to a 20-liter maximum.
Right, and we've explored the strict, sometimes completely paradoxical mandates placed on mechanical engineers. The realization that fire dampers, the very devices designed to save standard office buildings, will essentially build a bomb in a chemical laboratory. We've seen how QR sprinklers are mathematically engineered to carve out a 5-foot zone of breathable air, manipulating the room's thermocline so escaping occupants don't sear their lungs.
And we've unpacked the harrowing real-world stories that force the rules to change. The ATF tests proving that the Venturi effect can turn a simple plastic bottle into a 12-foot flamethrower. The exploding dorm room refrigerators, the catastrophic hydrogen blasts. Whether you are a venture capitalist pouring tens of millions into a new pharmaceutical facility, an HVAC engineer sketching ductwork schematics, or just a college freshman walking into an undergraduate chemistry lab for the first time, this code dictates the invisible safety net wrapped around you.
It really is a testament to the engineering community's profound dedication to learning from tragedy, analyzing the fluid dynamics and the chemistry of disaster, and translating those hard lessons into actionable, life-saving design.
I want to leave you with one final thought to mull over, something that isn't explicitly laid out in the 2019 text, but is the inevitable next chapter of this evolution. We've spent this entire time talking about human error, the panic, the synthetics melting, the wrong mixtures. But if NFPA 45 was written explicitly to protect human occupants from human error, what happens in the next decade? We are rapidly entering the era of AI-driven laboratories, fully automated robotic chemistry labs where robotic arms manipulate the reactive metals, sequence the DNA, and mix the hydrogen, running 24 hours a day in total darkness. If the primary objective of the code is life safety, how does the engineering change when the occupant isn't breathing oxygen, doesn't panic, and runs on lithium-ion batteries? How will the fire code adapt when we remove the human acrobat from the equation entirely? Next time you walk into a hospital testing facility or a high school science classroom, look up at the sprinklers on the ceiling, look at the exhaust vents humming in the background, look at the way the floor is sealed, and ask yourself, what hidden lesson learned from someone else's absolute worst day is quietly keeping you safe right now?